So yeah, photocopy machine. And so we learned a little bit about page here. No. Right. Yeah. So just a little bit of the background of the guy who invented it, a guy called Chester Carlson, back in sort of the 30s or so, and 30s, 40s maybe. Bottom right, you see like the first ever picture of a photocopy machine printout. And well, it's not really, maybe printout is going a little bit too far, I guess, as we saw in the video. Probably it's more, a little bit more like, you know, you have basically just an image that's coming from a another image that's imprinted onto the piece of paper, and then the black parts are just attracted by static electricity. So you know, it's hardly a machine at this point, but then it's sort of a proof of concept, so that you can see that the overall principle should work. So I guess the main difference to regular printing here is that everything is dry, right? So normally, if you want to make a printout, you know, there's some things which are wet that are involved, right? So you know, just with ink printing, of course, the ink is wet, and then you print it, and then you got to wait for it to dry. Same with photography. You know, you take your picture. I mean, not digital photography, of course, in the old school. Film photography, you have your film, and then you got to develop your film, and that again involves kind of, you know, chemical processes, so that you basically get the final image in the end. But all of these are basically, overall, they're kind of wet, right? So this you know, photocopy is kind of unique because it's actually a completely dry process. So sort of a little video over it just to get a little bit of a feel. This gave you a little bit of an idea of the working parts. So it involves this sort of photosensitive drum, actually so-called photoconductor, and toner, and basically the thing works with sort of static electricity, as we saw. But to break it down a little bit more, so basically the key component is this photoconductor, which is something that actually changes from an insulator to a conductor just by shining light on it. So when it's an insulator, the charges are kind of fixed, they can't move anywhere. But when you turn it into a conductor, then the charges are more free to move. And basically, this is the main working principle that is used inside the photocopy machine. So selenium is such a material, and basically it's sort of like a semiconductor material. And there's a trouble turning the page, such a simple thing. Okay. And the procedure sort of goes like this. So you have this photoconductor, and the first key thing to do is that you need to kind of sprinkle electrons all over it. And this is the action of this so-called corona wire. And then once you got this negative charges, then it tends to attract positive charges. Then if you imprint your image with light, then you get this pattern of charges, which is still completely invisible, but the charges are still there. And the charges sort of make up the image that you're trying to form. Then you put toner on it, which is positively charged. They get attracted to the negatively charged parts. And then by applying light everywhere, you get rid of the charges on the photoconductor, and you're just left with the toner. And then finally, you need to put the toner particles now back onto, not back onto a piece of paper, but transfer them onto a piece of paper. And the paper, you do this by basically charging up the paper with negative charge, which in turn attracts the positive charge. So you attract it onto the paper, and then finally you have a heater to fuse it onto the paper. So so what is this corona wire thing that they're talking about? And so this is where ordinarily I would have, you know, pulled out the demo, and then we would have played with this thing. But course, it's back in the office and we can't all go meet in person. So we have to sort of look at a few videos, and hopefully some of you have seen this kind of thing before. Usually it's like a kind of a sort of a toy or maybe a novelty item, but it's actually, got some sort of serious physics behind it actually. So it's this, sorry, a plasma ball is what it's called. And if you look inside what a plasma ball is made of, then it's basically this sort of high voltage source that's in the middle. So this is the thing that's in the middle here, this ball. And this is surrounded by some kind of gas like neon, argon, xenon, these types of things. And this high voltage AC source basically makes these kind of filaments, which are sort of flowing all from this AC, high voltage AC source to basically these ends here on the glass bowl. And you get these kind of nice kind of colors. And basically, what I was in the middle of last lecture is to kind of try and explain how this works. So we're on a little bit of a sidetrack, I guess. So originally talking about photocopy machine, now we're talking about the plasma ball. But making this plasma is a very critical component of the photocopy machine, and so that's why we're on this tangent. Okay, so watched a couple of videos about how this thing looks like. So what this guy was doing was to touch the sides of the ball, and then you can see like these filaments actually getting attracted to the fingers on the outside. So obviously one first question here is why do the what are these filaments getting attracted to? So when you put your finger on it, what is that doing actually? I mean, another question is, what are these filaments? It looks pretty cool, these things going out, but what actually is that? He did another little experiment where he's touching this audio jack of his phone, and then this is making some kind of buzzing noises. And so try to understand it. That is also part of this. Another interesting trick that you can do with these things is that if you get a fluorescent tube and you put it near these plasma balls, the fluorescent tube will actually light up. And this fluorescent tube is not connected to electricity at all, right? It's just, you just put it near it. So this is another puzzle that we're going to try and work through. In fact, this type of thing where you can actually power something electrically without any wires was actually Tesla's great dream. And this is kind of what he was trying to do research in. And so this is a sort of an example of something like that in action, although I guess as we know by now, wireless transfer of energy is actually pretty hard because, well, usually it's sort of maybe dangerous or impractical. So even though we don't use wireless power so much, of course, wireless communication is something we use a huge amount. So even though Tesla's dream wasn't exactly realized, still various applications are being used today. Okay, so we're talking about what is a plasma in the first place. Well, plasma is a kind of a phase of matter, if you like. So we all know solid, liquid, and gases. Plasma is when the electrons that are coming off the atoms are all kind of in this soup of ions and electrons, right? So normally all the atoms are neutral, right? So the atoms are generally a total zero charge, right? So these things like in ice or water or steam, all the underlying atoms don't have any charge, but here we've got a ionized gas. So basically it's a bunch of ions and also electrons. And so that's basically what a plasma is. And we can see a little bit more of why this plasma actually happens because, if you've got a high voltage source you basically got very high energy electrons in this terminal here. And these high energy electrons bump into these atoms, and they knock out electrons, right? And if they knock out electrons, then those electrons actually, there's another terminal here. So that's positively charged. The electrons want to actually try to get here somewhere. And the electrons get accelerated, and then they bump into another atom, and then that maybe creates another electron. So there's this cascade process where, I mean, if you wrote it as a sort of a chemical equation, it's not really chemistry, but well, maybe it is chemistry to some extent, but you've got electron and say a neon atom, and then you get another electron with a positively charged neon ion. Yeah. Okay. So so that's basically what a plasma is. It's this kind of soup of ions and electrons. Now, well, we could obviously see from here that how do you make a plasma? Well, basically you need a very high voltage source, right? So if you do this, this kind of cascade effects happens, and then basically you have this kind of plasma region. So in this region of this negative terminal, you have surrounding it kind of this plasma that's formed. So that's how you would make it. But in air, so I think this is roughly where we, no, actually, we got up a bit further actually. So in air, it's about 30,000 volts to cause the air to actually break down electrically. Right? So obviously you might think, okay, well, 30,000 volts, then just that makes plasma. But it's actually 30,000 volts. There's a distance involved too. So it's not just 30,000 volts, it's 30,000 volts per centimeter. So it basically means that you need to have two terminals, and if you can separate it by 1 centimeter, then you need to apply 30,000 volts. But if you separate it by 1 millimeter, actually you only need 3,000 volts, right? So actually the distance sort of matters. And a better way to actually understand this is not so much volts per centimeter, but more as a so-called electric field. So what's an electric field? Well, it's a, you can think of it as sort of the map of a force that a charge would experience around, say, another charge, or basically anywhere, right? So actually, in the end, in physics, we actually think of the electric field as really more important quantity rather than force. It's a bit of a chicken and the egg type of thing, because I mean they're so closely related. But basically, you know, we in physics eventually we think of sort of the field as electric field to have the real physical, you know, presence or entity. So we kind of think of this as being real, and then the force is just something that arises from it. Right? So if you have a positive charge, then the map of the forces kind of look like this, because all the positive charges, they want to get away from the positive charge, so it's sort of spreading out like this. It gets weaker as you go away and stronger as you get closer to it. For negative charge, just the same thing, but the directions are equal. So we can think of the electric field actually as a gradient in the voltage, meaning that it's sort of like the it's how whoops, what's happening? Yeah, so we can think of the electric field also as the force per unit charge, but we can actually equally think of it in terms of it turns out that it's the same units as volts per meter. So it's like how many joules of energy does like 1 coulomb change in 1 meter. So for example, if you've got like these two plates here and they're separated by some distance here, and there's some voltage between them. So you would say that, okay, these two plates have voltage difference of some value, let's say 1,000 volts. Now, basically, the electric field, another way to think about it, turns out, so it's not completely obvious that these are the same, but another way that turns out, if you do look at the maths, another way to think about it is that it's actually sort of like the voltage per distance across these plates. So if you separated this by 1 meter, then basically that would have a stronger electric field than if you were to separate it by a larger distance. I think we've got a picture of this here. Sorry, just want to go back to full screen. Want me to do it? Why not? Well, I don't have to do, I guess. So yes. Okay. Yes. All right. Yeah. So if you, for example, have your hand and it's charged at 30,000 volts, and this, this doorknob is at 0 volts, then the closer that you move your hand to the doorknob, basically the actually the stronger the electric field is actually going to be, because we can relate the electric field to basically the slope of this line. So you can imagine that you bring your hand in, and the closer that you'll get to the door, basically this slope will be larger and larger. And so the electric field will become actually stronger and stronger as you bring your hand close to the door. And basically at some point, the electric field will be strong enough such that it will cause a spark. Okay, so this is maybe a better way to think about how sparks happen in air, which is that and it basically tells you that the dependence it has on the distance. It also tells you that the shape of the thing matters. So if you have a pin like this, then actually this has a different kind of dependence with the distance. So if you've got a pin here, then the voltage actually drops faster, and because it's related to the slope, it actually will have a stronger electric field at this point. And so in this case, if you're holding a pin, then even though the distance might be the same, you might actually already get a spark at this point, whereas with the same distance, maybe you have to put your hand a bit closer before you get that spark. So if you want a nice big spark happening, then what this tells you is that you should walk around in winter holding a pin, and then you might see a big spark. Okay, so maybe that's maybe where we got up to last time. Yeah. So so that's a bit of a recap, but so it's kind of another application of this same thing, but actually lightning rods are kind of application of this idea. So most people think that lightning rods are just things that you put on the building so that when lightning strikes it, it will actually strike that part of it, and then it's all connected to the ground, and the lightning, the electricity from the lightning will not, will go through like the wire, as opposed to going through the house, and maybe whatever it's in there, it'll disrupt your electrical circuitry inside your house and do bad things, right? So that's certainly true, but actually it also has another function, And if that was basically the only function, then the shape of this wouldn't really matter so much. But there's an interesting kind of effect that it's called St. Elmo's fire. If I can get to the next page. Yeah, St. Elmo's fire. So this is an interesting phenomenon where I think, well, maybe I should check this, but if you have a something like this ship here, and you have these masts, and the masts are, sailing ships usually have these masts which are very high and they tend to be a bit pointy, right? And so what people saw was that you see this kind of corona discharge, and this corona discharge can be sort of a little bit like the plasma ball that we saw, but maybe slightly different colors. And basically what's happening here is that because of the very pointy shape of these masts, they tend to actually form this kind of plasma much more easily around it. And so you have this kind of cool effect where in the ship's mast, you have these kind of glowing tips, right? Maybe I have a picture here actually, which I didn't quite prepare, but let me see if I can get it, but I was having so much trouble with containing. So I have this link here. I noted down, which I didn't prepare before, but let's have a look at what it was. Okay. Yes, so I think this was going to be a picture of this actual phenomenon. Sorry, I should have prepared it beforehand, but yeah, I can't seem to get the link to work. I'm sorry. Okay, all right. So let's just skip that one. But basically, this corona discharge has lightning rods has the effect of making this kind of corona discharge, and in fact, this actually kind of has the effect of making the lightning actually actively strike the lightning rod as opposed to other things. So because of this kind of very pointy shape of the lightning rod, the lightning is actually very attracted to it because the electric field around it is causing basically this area to becoming this kind of corona plasma. And this means that the lightning has a much more easier path towards ground. So it actually actively kind of attracts the lightning to it because of this kind of very pointy shape. Okay. All right. So that's basically the effect of kind of this plasma. But there's another kind of puzzle that we haven't really sorted out, which is that, well, this thing makes these, all these colors like purple and stuff like that. So basically, what is the origin of these colors? So these colors are actually basically they originate from the same reason that we have different colored. Well, we call them all like neon lights, but actually the neon lights that we kind of see are actually different types of gases, not necessarily neon. So by changing like the gas inside the tube to things like argon, krypton, xenon, you can make all different kind of colors for the neon lights, right? They're not actually necessarily neon. So neon makes this kind of orangey red kind of color, but other types of gases have different colors, and so it's quite kind of beautiful. So I think this kind of purple one that we have here, this purple plasma ball that we're talking about here, actually this is the same color as the one that is in my demo, is basically argon based. So this one has argon inside it. That's why it makes this purple thing, purple kind of color. Now, so why does this actually make these colors, right? So this is another question. Does anybody want to take a guess at why you have different colors for different elements when you put them in this tube?
The energy of the light is different.
Yeah, that's good. So the energy of the light is different. Yes. So so the energy of the light is related to the frequency of the light. So obviously different colors mean different frequency, and different frequencies, as you said, means different energies, right? Yes. Then why would say neon have a different energy light to argon? Like what would be different? Any guesses?
I don't know, like wavelengths of the light, I guess.
Yes, yes, but yes, that's right. But I think that's basically what we were just saying. So the frequency or the wavelength of the light, as you say, is different, and that's related to the energy of the light. But you know, why would the argon or neon have maybe different energies? And also another thing is, you know, this type of light, you know, it just looks kind of a bit different to, say, light that we might get out of a, you know, old-fashioned light bulb, right? Old-fashioned light bulb, it's like, you know, just like this, you know, white or orangey color, and you know, you can get different types of light bulbs, and it's not necessarily like this pure red or this pure purple color. I mean, it obviously looks a little bit different to normal, well, light bulb type of lighting. I mean, any ideas on why that might be?
Electron affinity, I think.
Okay, yeah, that's an interesting idea. Electron affinity, so to attract electrons, yeah, more or less. Yeah, so yeah, I mean, I never thought of it in that way, but there might be a way to think of it like that. But basically, yeah, we'll come back to this point in detail in chapter 13. But just to give you a sneak peek at why it might be different, basically, the thing with these types of lamps is that you have like these various gases and inside, and then you put a high voltage around it, and then they emit this particular kind of glow. And what this is actually taking advantage of is an interesting effect where if you've got an atom, basically the atom, I can just draw something. Very difficult. Okay, here we go. Just use my finger here. So if you've got an atom, basically the electrons around the atom, turns out that there's only like certain different sort of orbitals, and a little bit like, you know, atom, we can think sort of like our solar system, right? So there's something heavy in the middle, which in the solar system is like the sun, and then you've got these planets revolving around, right? And if you think of like where the planets are, now there's not really any restriction on like where the planets can be, right? Because if you just got a planet and then, you know, this orbit that it takes, it just purely depends upon, you know, a few things like basically like how much energy that the planet has and so forth. And so if you changed the speed of like this planet, then it would totally change the orbit, right? Now, in an atom, it's interesting that it's kind of a bit, it's quite different. So turns out that there's only a certain sort of number of different orbits that the electrons can actually take. Right? So there could be, you know, in an atom, you know, it could take, say, this orbital, or it could take this orbital, but it couldn't really take something in between. And this is actually what this is sort of the discovery of quantum mechanics. And quantum mechanics, basically, people found out that actually, when you look at things which are very, very small, you can't have, let's think of the name quantum mechanics. So well, at least in English, so quantum, this word quantum comes from the word basically quantized, right? Quantized basically means that you can't have certain well, you know, values of certain things are kind of discrete. Right? So instead of being continuous, it has to be discrete. So it has to be only this or this or this or this, and it can't have something in between. And so basically the reason why these colors are so pure is because they're actually related to, as some of you correctly said, it's related to the energy of the light. But it's basically, you get these pure kind of colors because it happens when, like, say, an electron in this orbital jumps down to another electron in a low orbital. Now, this has some energy, say energy 1, and this has some energy 2. And then basically the color that's coming off it is related to the difference in energy between those two orbitals. And now, because this E1 and E2 can't be any number, it can just be only like some particular quantities. This is why the colors are very pure like this. And you have, you know, these only some particular wavelengths coming off of this. And so this works in a very different way, actually, to regular light bulbs, where in a regular light bulb, the heat, it's actually, you just basically heat something up super hot, and then once you heat it up very hot, then it glows, because, you know, if you heat up something, as heat up a piece of metal, you know, initially it glows red, but then if you heat it up even more, it'll be like sort of glowing white. And that works on a completely different principle. So yeah, so basically we'll talk about this a little bit more in the later chapters, but you know, it comes from the fact that yeah, the energies are kind of discrete in an atom. Right. Any questions before I just erase this? Okay, so this, all right. Okay, so basically, so in this plasma ball, what's happening is that firstly, you have this high voltage source, and because it's so high voltage, it's actually ionizing the gas inside this plasma ball, right? In this case, it's like something like argon. And then once it's ionized, so you have all these electrons and argon atoms, it's ionized, and you put this high voltage through it, then you basically have this particular sort of effect where the atoms actually are releasing, you know, going down in energy and then releasing light. And because it's of a fixed frequency, it comes out as this kind of very beautiful you know, single color. So, well, that explains to some extent how a plasma ball works. now some more puzzles. So if we go back to our example. Might like to actually rewatch that video a little bit because sharing the right screen. Yeah, so what we're seeing here is that so the guy's touching the side of the ball, and then it's making so it's making these filaments. So basically all these filaments that we're seeing here are actually ionized argon that's actually there because you have a high voltage. And then the light that you see is actually because you have this electricity that's actually flowing through it, and that's actually exciting these argon atoms into some higher level, and as it releases that energy, it just emits that particular kind of light. Okay, so now the next puzzle here is, so he's touching the sides, right? Touching the sides. Now, apparently these filaments are attracted to his hand, right? Anybody have any idea of why these things will be attracted to his hand? Nope. Okay. All right. No problem. So let's go back to this. Let's stop the video first. So go. Okay. So basically what's happening when you touch the hand, I mean, it's tempting to think that actually you have this high voltage source, and then it, like lightning, your hand is forming a path, right, back to the ground, right? Because a bit like how lightning, it's basically it's highly charged clouds, and then there's the ground, and basically this huge charge imbalance, it's trying to neutralize it, right? And so basically if you happen to be sort of standing in the way, then the electricity will pass through you. But that doesn't quite explain it in this case. Well, it sort of does, but it doesn't completely explain it, because this glass is not conducting, right? This glass does not pass any electricity through it. So if it doesn't pass any electricity through it, then you might think, well, how could this possibly be affecting anything? Because if it's electrically insulating, then where is this going, right? Because you got this like spark basically that's going from the inner globe here to the edge, but this is insulating, so well, it can't flow through. I'm sort of giving you a hint, I guess, already with this diagram, but can anybody take a guess, or offer any ideas of why, even though this glass is insulating, actually these filaments or the sparks would be still attracted to the hand? No takers? Well, okay, so the key thing here is that actually, this is an AC voltage. Okay, so I mean, normally it's just much easier for you to think in terms of DC because you have a circuit and just the electrons are flowing, right? And actually, even for the kind of things that we use every day, right, in our appliances, actually the voltage that comes out of our walls is like 50 hertz or 60 hertz, depending on the country. But actually, 50 or 60 hertz is actually pretty low frequency, right? I mean, it's oscillating, okay, 50, 60 times a second, but compared to, I think, the frequencies of this Tesla coil that we have in the plasma ball, it's like much less. Actually, I can't remember the frequency of the AC frequency, but it's extremely high. It's like I forget, maybe let's say it's thousands times higher. So when you have an AC voltage, it actually works in a little bit of a different way. You got to change your thinking a little bit, because when you have an AC voltage, actually, no charge really flows around the circuit, right? So if you draw a circuit like this, and it's AC, so normally, we're thinking of a circuit sort of like this, right? So we've got a battery, and then we've got maybe like the light bulb here, and then basically what you think of is, yeah, the electricity flows like this, and that's why you need a complete circuit in order to have a something electricity flow. But when you actually have AC circuit, AC voltage, alternating current, basically what happens is that electricity is actually it's going this way around, and then it goes around the other way, goes this way, goes the other way, and it kind of keeps on repeating this this cycle where it goes this way, that way, all the time. And in terms of just the regular light bulb, this is why it doesn't really matter so much that whether it's AC or DC, because this light bulb doesn't really care whether it's flowing left or right. So it will light up either way. And so, yeah, in this case, it doesn't really make a difference. So in the case of this, this plasma ball, what actually happens is that because it's an AC current, it's actually best to think of this as a sort of a so-called RC circuit. No, I can't say that for the moment. So let's try to understand what's going on. So basically, the best way to think about this is that, so we have this high voltage circuit, and this part where your finger meets the ball, and this filament or spark. So basically, when you've got those wobbly things which are going through the plasma ball, we can basically think of that as sort of some kind of conductor, right? Because this is all plasma here, and electricity can more or less flow along the filament, right? So and now glass actually is an insulator. So we can actually think of this part of the thing as a capacitor. So are you guys all familiar with the capacitor? Okay. All right. So you've done capacitors. Have you done anything on AC circuits, like resistor, capacitor circuits, things like this? Oh, you have. Oh, great. Okay. Okay. So if you have, then perhaps this might be already something that you've seen. But anyway, it doesn't hurt to do it again. So basically, if you think of this as a capacitor here, now there's a resistor here that's basically through your body to the ground, And then there's also another resistor here because this plasma isn't really a perfect conductor either. So we can kind of think of this as basically an RC circuit. And RC stands for resistor capacitor circuit. Okay. And so I think it helps to actually just do this. So can I get everybody to do this? So we have a bit of a class activity. So go to your browser and type in this circuit construction kit AC FET, something like that. And then go to the link. I mean, not go.
Can you please copy paste the link into chat now?
All right. Yeah, that's a better way to do it. All right. There we go. All right, go to this link. What am I sharing here? Okay, so everybody got to the link page, and so I think if you go there, there might be like 3 options, and then you have to choose the one that says like RC or LC circuit. Let me do it again myself so I can show you. So you go to this FET, active interactive simulations. Okay, and then in the middle there's this RLC. So choose that one. Then you'll have this thing. Everybody got there? Can I get a show of hands so that I make sure that everybody's actually got to this site? Okay, good. And keep your hands up because I'm sort of waiting for everybody to do it. Okay, all right. Okay, I think we've got more of you there. Okay, so now what I'd like you to do, maybe I'll just share my desktop now because okay, so basically what I want you to do now is to make this circuit here. And so making the circuit is quite easy. Basically all you got to do is like drag and drop certain wires. So what we're going to do here is to just make this RC circuit, right? Okay, so what an RC circuit consists of is this AC power supply, and then it's got a capacitor, and then it's got a resistor, and then you just make a loop like this. Okay, so we can do this together. Bale, do you have a question, or did you just okay, you're just raising your hand from before. Okay, so we can all do this together. So just make sure I'm sharing the right screen. Okay, we're good. All right, so firstly, just get your AC voltage supply. So just stick that there. So I just dragged and dropped from over here, okay? And then we can get a resistor. Okay, and then you can just join the resistor there. Okay, and then you get a capacitor. Just join the capacitor there. And then get a piece of wire because we need to connect all these things. So get a piece of wire and then connect it to the AC source there. And well, I'm gonna make a triangle here because otherwise it's hard to see what's going on. Okay, so get another wire there and connect it like that. All right, so let me just wait until everybody does that. And so if you finish that, just do a thumbs up. Okay. All right, I think most of you got it. Okay, so you can change a few things about the circuit, such as the resistance. So, for example, if you change the resistance something higher, then you can see actually. So the blue dots here are the electrons in the circuit. So you can see how making the resistance higher, the electrons don't move as much. So low resistance like this. So I don't know, like 4 ohms or something. You can see that they're sort of going back and forth. Now this capacitor, we can also change the size of the capacitor. So if you make it a bigger capacitor, then basically what the capacitor is kind of like a sort of a rechargeable battery, but then it doesn't store so much charge. It just discharges and charges very quickly. So you can see that in each cycle of the circuit, this positive and negative charges accumulate on these sides of the on these plates. So capacitor, simplest type of capacitor is just 2 pieces of metal plate, and there is nothing conducting in between these parallel plates. So it's just, well, it could be air or some material between it, but it's not a conductor. So basically, you have like plus and minus charges. And if you make it like a large capacitor, then it will oscillate more, whereas if you make it small, then it doesn't oscillate so much. And then here, I think you can turn up the voltage. So as you might expect, if you turn up the voltage, then it will start to oscillate much more wildly. And then now things are on fire. If you go to very high frequencies, then the electrons are going back and forth. So there's an advantage of a simulation. You can make things catch fire, and it doesn't really matter. Okay, so so basically, I think this gives you a pretty good idea of what a LC circuit basically does. It if you connect it to an AC power supply, then basically it will just oscillate like this, right? It depends on the actual parameters of the resistor and the capacitor, but basically it will kind of oscillate in terms of the current. Okay, so does everybody make their circuits work? Okay. Okay, good. All right. Okay, so that's basically these RC circuits. So all right, so now that we've got that kind of understanding there, now we can go back to this and maybe understand what's going on here better. Sorry, I need to go back to my slides. Yeah. So we can go back here and we can sort of understand a little bit better what's actually happening. So, we see what an RC circuit does. So what we've got here is basically the same. We've got an AC power supply, right? So that's just like our power supply that we had here. It's very high voltage, very high frequency, but it doesn't matter, whatever. We've got basically this finger that you put on the side there, and this filament basically forms a capacitor because this thing is an insulator. So glass doesn't conduct any electricity. And then these things are resistors. So, basically got an RC circuit here. And, this is all connected to ground so that it's, form this loop like this. So basically what we saw in the RC circuit is that even though this glass is an insulator, it doesn't conduct any electricity, still basically, current will actually still form. It'll go back and forth around this circuit, and if it's a high frequency circuit, then it'll do this extremely quickly. So it'll go back and forth, back and forth. Now, so what this basically tells you is that even though this thing, it doesn't conduct electricity, it's completely an insulator. But actually, it doesn't really matter in this case because you're basically forming this capacitor here. And if you've got a current that is going back and forth like this, well, that's still an AC current. So despite the fact that you don't really have any conductor here, you still will have an AC current. So even though you would not be able to make a DC current, like, with a battery, because you've got this insulator here, with an AC current, this does not stop you from making an AC circuit and an AC current. So basically, your finger, yes, it does form a conducting loop, basically to the ground, and it's just that this will be an AC current, not a DC current. So, in the end, it's kind of right. It's, what we said before is kind of right. Basically, you have this high voltage source that wants to, get back to ground, and it's trying to form the loop. Now, just our thinking is just, so much more used to DC that, it looks impossible, but actually, it's perfectly possible if you think of it as an AC. Any questions? Okay, no. Alrighty. Then okay, so actually we've basically already done this. So basics of RC circuit. So if you plot the current and the voltage, then it'll look something like this. So if you've got a oscillating voltage, then it will be oscillating current too. The actual values of how much current you have will be dependent upon the actual values of the resistor and the capacitor involved. So anyway, this is just a little bit of maths if you're interested, but not really necessary to understand. Okay, so hopefully a lot of this has sort of answered some of the questions that we originally posed for the plasma ball. But still there's maybe a couple more questions. So this is again where I would be doing a demo, but again, I really can't do it. So now we've talked about how basically these filaments are attracted to you, but suppose we do this type of experiment. So if you touch the side of the plasma ball, then actually what you'll see is the filament will actually sort of repeatedly go up and down. Whereas if you touch the top, it doesn't really do this very much. So let me kind of demonstrate that, of course, in a video. Okay, so go back here. Let me turn this guy off now. So I'll go back to find the right spot where, yeah, so right about here. So notice here how this guy, when he's got his finger on the side here, you see this kind of, it's not so easy to see here. Yeah, actually just right at the end there. What you kind of saw is that the filament is sort of, it seems to be sort of rising, breaking, coming back down, rising, breaking, coming back down. So I don't know, maybe I can do this in sort of slow motion. Go back a bit. So when he's doing this, right at the end here, so you see it's going up and then coming back down. It's going up, breaking, coming back down, going up, coming back down. So I hope you can just sort of see that in the video there. Now, why would the filament sort of always be sort of going up and down like this? Anybody want to take a guess at that? No idea. Let me think of a hint that I can give you. Okay. I mean, so what do you think happens to the gas when you got this? I mean, this is basically a sort of a high voltage and, quite a lot of electrons going through. When you have like a, piece of wire and then you put a lot of current through it, what happens to that wire? No idea? Okay, what do you think? I'm just going to pick somebody at random now. I'm sure this is going to scare you, but okay, Hanjing, what do you think happens when you put like a lot of current through a wire? What happens to the wire?
Oh, and I guess there must be high voltage, so like the
You can just name anything that might happen to a wire. Say you've got some current and like you just put like a lot of current through a piece of wire, what might happen? Any idea? Anybody want to help out Hanjing? How about you, Ella?
I think there might be, you see when the finger touches the plasma ball, there forms a capacitor or actually forms a circuit. I think maybe after a while, there might be the process of the capacitors to discharges and the circuits was cut open.
Okay. Okay, that's an interesting theory. Okay, all right. Yeah, well, okay, but in that case, when we did our little demo, actually the current did change direction, and so I guess you could say that the current does stop at some point, but it does keep on going. So, okay, well, it's an interesting idea. Any other ideas of why it might sort of, well, why don't we just go back to a simpler case, or my hint. So if you just got a regular wire and you put a lot of current through it, what might happen to it?
The wire might melt at some point because it's had resistance, and if you put a lot of current onto it, and you generate a lot of heat. So which cause the wire to melt.
Yes. So it will heat up. Okay, so that's my hint. Exactly. So thank you, Boyan. So if you have a lot of current going through this side, it will actually probably heat up this this filament, right? Now, so that's my hint to you, right? But so now can somebody sort of explain like why you might see this going up and then coming back down, going up, coming back down?
gas blows up.
Yes, beautiful. Yes, that's exactly right. So basically, what's happening here is that current is going through, and then it's actually heating up that gas there, right? So it heats up that gas, and then because it's heating up, hot air rises, it'll rise up. But then, if it rises up, then it's becoming sort of out of contact with the it's getting further from basically the finger in the central Tesla coil there, and then basically it'll just break, right? And then it'll reform at the bottom, go up and break, reform, go up and break. So that's exactly right. So thank you for that, Yushuan. That's exactly basically the effect that we're talking about. Okay, all right. Well, thank you for the participation there. I don't always like to sort of call on people. It's sort of a bit terrifying, but I appreciate that you can sort of give your ideas here. Okay, I think it's sort of about time maybe to wrap up. So maybe we can leave it there, and we can continue on. But next lecture, any questions just to finish up? No. Okay. All right. Then I will see you on Wednesday, and see you then. Thank you, everyone.